Hiya. It's really nice to meet everyone. Thank you so much for hosting us for this talk, and also thanks to the Represented Initiative, which kind of paired us with this brown bag series to give our talks that we missed giving at WIST. So to begin, I thought I'd just take an opportunity to quickly introduce myself. My name is Maxine, and I've been a PhD student at HCIL since 2023. I really love 3D printing, art, and music. And in my work, I build simulations and testing-based design tools for fabrication. And now for the rest of my PhD, I'm particularly focused on sustainable fabrication. But in the past, I've worked on a variety of different types of 3D printing projects, from optimizing microstructure metamaterials that you can 3D print at the size of a speck of dust, to creating 3D printable view-dependent appearance, and also soft robotic modules that are 3D printable and can locomote independently and collectively. And my background is in graphics, and now I'm kind of transitioning to HCI, so I'd really love to hear everyone's perspectives on kind of computational fabrication and HCI and that intersection. So today I'm going to be presenting SustainaPrint, which is a project on how to make the most of eco-friendly 3D printing filaments when you're doing different 3D printing tasks. So 3D printing produces a lot of waste. In fact, previous work estimates that about 1/3 of all 3D printing material in FDM 3D printing is discarded as waste, which can contribute significantly to environmental issues. We can kind of see this if anyone here has worked with a 3D printer before. You've got your support material, you've got all of your spaghetti attempts, failed spaghetti attempts, kind of prototypes, test pieces, and kind of that nature of like iterative prototyping. And PLA, which is the most common 3D printing filament, is marketed as biodegradable, and it technically is biodegradable, but only if it's heated to very high temperatures. So in a landfill, it can take between 100 and 1,000 years to break down, which makes it much less sustainable than it actually seems. So people might think, okay, I've got my big bucket of waste here, I can throw all my supports in, it'll like degrade, but it won't really. So we kind of want to ask this question: how can we facilitate the use of maybe recycled material or eco-friendly material that is more biodegradable into 3D printing? So, for example, one way to kind of improve this waste or the impacts of this waste is by recycling filaments. So you can melt down all of your scrap filament and re-extrude them. In kind of a lab setting, you could do it with a machine like Filabot, or you could use, much larger industrial equipment to do this. And this can help close the loop and reduce demand for new virgin plastic. Alternatively, you can explore like more biodegradable filaments. But often these kind of eco-friendly filaments face mechanical degradation. So previous studies have shown that when you kind of make this process of melting and re-extruding filament, the strength reduces each time, and it can drop by nearly half after just a few recycling cycles, which makes recycled filament risky for load-bearing or functional parts. And at the same time, other types of eco-friendly filaments also kind of have this degradation sometimes if they're made of biodegradable materials. And previous work has kind of tried to tackle all of these issues through a variety of different angles. So some work has been kind of focused on geometry. So how can we change the geometry of what we 3D print in order to reduce waste and improve sustainability? For example, with wireframe prototyping or reusing existing objects like Scrappy. There's other approaches that are kind of more material science focused, like developing biodegradable filaments out of like coffee grounds or other types of biodegradable materials. But again, as discussed, these often trade off on strength. So our work sits at this intersection of geometry and materials. So we combine geometry-aware simulations with material-aware assignment. So we take an object and we look at the weak regions And we can reinforce those weak regions with, new virgin filament that maybe is less sustainable but more strong. And then the strong regions of the object, we can kind of maximize our use of weaker eco-friendly filament in those areas. So our workflow is relatively simple. The user loads an input model, and then they use our UI to simulate forces. Right now, for SustainaPrint, it's a pretty simplified UI, although I think in future work, kind of extending the different types of like load setups that users could use would be like a valuable direction. And then our model basically segments the object into strong and weak regions and exports a dual print file that the user can then actually 3D print and kind of try to minimize their use of virgin plastic, but also maybe compromise a little bit less on strength if they had printed the whole thing in a weaker eco-friendly filament. So the core of our method is basically simulations. We use finite element analysis, and we run stress simulations to identify high load regions in the model. And then we offer two different segmentation strategies, one which is more fine-grained. So we take all of the high-stress tetrahedrons from the model, and we basically say, print these in strong filament. And then the other is kind of layer aligned, focused on looking at those high stress regions, but also not being as fine grained, which can kind of reduce printability, as we learned through like many iterations of trying to print these objects on the printer. And then we also have some additional heuristics to improve printability of these dual material prints. For example, we can remove small islands of strong filament and reassign them to weak filament, or vice versa. So kind of prevent the nozzle from having to switch out too often, and also apply a uniform outer shell to the object if they want to maintain kind of a nice aesthetic, like uniform color on the outside of their print. Another challenge that we faced during this process was adhesion between filaments, where at the beginning of our experimentation, we found that even if we print with stronger materials in some regions and weaker in others, the prints would just break at the regions where the two materials are connecting, because sometimes these materials have different melting temperatures, and also the kind of slicing pattern varies at those like kind of layer lines, and might change direction and, reduce adhesion. So we use a zigzag pattern at these intersections. It's actually a built-in option in Ultimaker Cura if anyone ever has this problem. It's like an experimental feature in the advanced options. It actually took me a long time to discover this option existed. And there was also a lot of prototyping of other approaches to this. And this kind of zigzag pattern increases contact area and prevents delamination. So it can actually make our hybrid print stronger than our weak baselines. And then we do provide a UI to users that guides makers through the process of setting up their print for dual material optimization. They can specify the materials, load regions, apply different force directions, and then preview their segmentation. And one of the key things is they can move a slider that says, I want to use 70% of virgin filament or 20% of virgin filament. So they can kind of explore how changing that threshold changes the material assignment. And, we have tried it on a variety of applications, including like hooks, which are reinforced at kind of high stress regions, plant pots, bottle openers, and stands for various devices. And we also test these with the Instron machine to check if they're actually stronger than if you had printed the entire thing with eco-friendly material. So to kind of evaluate our method, we use the Instron and we take a variety of different test objects and we print them in an eco-friendly baseline, SustainaPrint, and then the entire virgin material, which is kind of like the best performance that you would get. And for our eco-friendly baseline, it's actually very hard to find like recycled filaments that have data sheets. So we use Polyterra, which is a biodegradable filament that kind of also suffers the same degradation effect, and that it's like kind of weaker than our baseline of tough PLA. We also use PLA. You can see, we have 2 strong baselines in the paper if you want to see more results there. And we print them kind of with 20%, 80% balance of sustainable to virgin material for the SustainaPrint. We tested the functional objects that I already showed, and also some primitive shapes, hook, chain, beam, cylinder, and a dome, which is kind of meant to get a bit of a wider picture of like the different types of torques and kind of specific scenarios that, might lead to different failure cases. And we found that on functional objects, SustainaPrint improved load capacity in the best case up to 78%, with an average of 22% gain compared to fully eco-friendly prints. And toughness increased by nearly 20% on average, but some objects showed much higher toughness. Now, as you'll notice, not all of these results kind of go in the same order, and I think that there's a lot more work to be done in this entire direction on accounting for additional stresses that come from the 3D print toolpaths themselves, because right now we treat each of the materials as like a homogeneous plastic material, which isn't actually what's happening. So for kind of my next work, I'm working on homogenizing the 3D printed toolpaths in order to get kind of better simulations. And for the primitives, it's essentially the same story. Boost strengths by about 20% on average. And, if we want to look at kind of a case study of the actual kind of mechanical behavior, as opposed to just kind of the static numbers, let's look at the tripod plant plot. And we see on the left, it printed entirely in our virgin strong baseline. In the middle, SustainaPrint, and on the right, in eco-friendly filament. And then these images are kind of showing the first failure modes. And on the eco-friendly kind of case, it's a very brittle filament, and the legs just immediately snap off. If you look at the kind of load extension curve, you can kind of see that catastrophic failure. Whereas with the tough PLA, the failure is much less catastrophic and the curve is more smooth, and SustainaPrint kind of takes on a more similar profile to the tough PLA because in those critical regions, it kind of has the behavior of the strong filament rather than the weak ones. And then something that we also wanted to discuss was kind of trade-offs from dual material printing, because again, if you've worked with dual material printers, you probably know that the prints take a little bit longer. And if you have a print with a single nozzle, there's also all these purge towers, which produces extra waste. So, our method we evaluated on an Ultimaker S5, which doesn't have purge towers. But with purge towers, waste can increase by 37%. So it's an important kind of caveat of the method of it's very dependent on the type of 3D printer that you use. And another thing that, I really want to kind of keep working on, how to kind of take this method and make it more compatible with single nozzle multi-material printers by trying to minimize material changes kind of throughout the process, which is what leads to the purge. Then, as I mentioned, a lot of these eco-friendly filaments don't have mechanical data available, especially if they're kind of recycled, where each batch may vary. So, some companies do have recycled filament that they sell, but the mechanical performance varies depending on which month you buy it. So we also created an at-home mechanical testing toolkit so that users can take their recycled eco-friendly filament and try to characterize it and decide, whether they want to use SustainaPrint or whether it's strong enough on its own, or maybe it's so brittle that it's not even worth using. And they basically print this little testing tool, and then they can use various different amounts of weights and kind of at-home objects, luggage scale, to figure out when these different bridges break and decide, whether they want to use the filament. We validated our mechanical testing toolkit against available data sheets for different filaments, and we're able to kind of capture the the same story that we've seen in previous work for tensile strength decreasing with number of recycling cycles and get between one standard deviation of some special recycled filament that was sent to us by a partner company. So, limitations and future work. I guess I've already mentioned a lot of the limitations throughout the presentation. But we currently really require dual extrusion printers and user-specified boundary conditions. So really, I want to focus on how to address this problem of material changes and additional purge waste. But not only that, but kind of view sustainable fabrication more holistically, because so many prior works, at SustainaPrint don't consider energy consumption, and maybe other methods that could be used to maybe avoid all of this waste in a kind of cleaner way, by rethinking kind of how we prototype and kind of how we engage with fabrication processes. And there has been some really exciting work recently at Kai on kind of like separating mixed material 3D prints. I think that would be really kind of nice direction to also think about. And also just incorporate some more sophisticated kind of simulations methods and designs tools that, really take into account the layer lines and do proper material homogenization, as opposed to just viewing it as a homogeneous material, as we can see that there are like anomalies in our mechanical testing experiments. So I think that's it. So thank you so much for listening. It's very nice to meet you all, and I'd love to chat anytime. And yeah, thank you. And if anyone has any questions.